When an unstable atomic nucleus violently ejects a particle into the void, the resulting radiation often appears to be entirely spontaneous. Because we cannot predict the exact moment a single atom will decay, it is easy to assume the process is chaotic. In reality, radioactive decay is a heavily regulated thermodynamic transition. Every mode of nuclear decay is governed by a strict, overarching constraint, the Q value. The Q value is the exact mass-energy difference between the initial parent nucleus and the final daughter state. This value acts as a non-negotiable energetic budget. If a specific decay pathway demands more energy than the Q value provides, the laws of physics forbid that pathway from occurring. This energetic budget translates directly into kinematic reality, determining the exact momentum and velocity of any emitted particles. By evaluating the Q value equations for primary decay modes, we can use fundamental conservation laws to mathematically derive particle kinetics. Understanding nuclear stability requires tracking the strict mathematical conversion of mass into kinetic energy. The driver of this instability is the ratio of neutrons to protons, or the N/Z ratio. In many nuclei, the N/Z ratio is too large, meaning the nucleus is neutron-rich and unstable. To correct this, the nucleus undergoes beta-minus decay. A neutron converts into a proton, releasing an electron and antineutrino to conserve charge. We calculate the energy released using this equation for the beta-minus Q value, subtracting the daughter atom's mass from the parent atom. The emitted electron's mass isn't subtracted because it's already accounted for. The daughter's atomic mass includes the extra orbital electron required for neutrality. Conversely, some nuclei are proton-rich, meaning the N/Z ratio is too small for stability. These nuclei can undergo beta-plus decay, where a proton converts to a neutron while emitting a positron and a neutrino. In this equation for beta-plus decay, the math changes. The Q value includes a specific penalty, -2 times the mass of an electron. Ejecting a positron forces the nucleus to shed the mass equivalent of 2 full electrons. This is the thermodynamic cost of the transition. If a proton-rich nucleus lacks the mass-energy difference required to pay this 2-electron penalty, beta-plus decay becomes energetically impossible. To bypass this limit, the atom utilizes electron capture to correct the N/Z ratio without the positron mass penalty. The nucleus captures an inner orbital electron, typically from the K-shell, to convert a proton into a neutron. Because the electron is captured rather than created and ejected, the 2-electron mass penalty disappears from the Q value equation. While this solves the energy deficit, removing an inner electron creates a vacancy in the atomic shell. Outer electrons immediately drop down to fill this K-shell vacancy, emitting characteristic X-rays as they settle into lower energy states. The choice between these pathways is determined by the available Q value budget. After an alpha or beta transition, the daughter nucleus is rarely in its ground state. It is usually left in a temporary, highly excited state. The nucleus sheds residual energy through gamma decay, emitting photons to reach stability without changing its atomic mass. Cobalt-60 illustrates this multi-step descent. This diagram maps cobalt-60's transition to nickel-60. First, beta-minus decay drops it into an excited state. Next, a 1.17 mega-electron volt gamma ray is emitted. Finally, a second 1.33 mega-electron volt gamma ray allows the nucleus to reach its ground state. These photon emissions ensure that the total energy released by the nucleus aligns perfectly with the initial Q value prediction. Heavy nuclei relieve extreme mass instability through alpha decay. In this process, the nucleus ejects an alpha particle, which is a helium-4 nucleus consisting of 2 protons and 2 neutrons. The mass difference between the parent and products defines the total energy, Q, available for the decay. Knowing the total energy Q, we can determine how that energy is partitioned between the recoiling daughter nucleus and the alpha particle. We can derive this partitioning by applying 2 fundamental conservation laws. First, conservation of energy states that the sum of the kinetic energies of the alpha particle and daughter nucleus must equal the total Q. Second, conservation of momentum requires that the resulting momenta of the 2 products be equal and opposite. Since kinetic energy equals momentum squared divided by twice the mass, these energies are inversely proportional to the masses of the particles. This creates a ratio based on their atomic mass numbers. A-4 for the daughter nucleus, and 4 for the alpha particle. Solving for the alpha particle's energy relative to the daughter, we find that K-alpha equals A-4 divided by 4 times Ky. By plugging this into our energy equation and finding a common denominator of 4, the numerator simplifies to A, leaving A over 4 times Ky equals Q. Isolating Ky as 4 over A times Q and substituting it back into our ratio gives us the final result. The alpha particle's kinetic energy is exactly A-4 divided by A times Q. Because the alpha particle's mass is very small compared to the total mass A, this fraction shows that the alpha particle carries away nearly all of the available Q value energy. By knowing this starting atomic mass and the calculated Q value, we can mathematically dictate the exact kinetic reality of the resulting radiation.